You're in the lab with your mate JJ. Today is Learning the Art of Electronics Day. Today we're going to keep on keeping on with the Learning the Art of Electronics. It's Tuesday. Today's silly job title is the Switch Switcher. I'm the Switch Switcher. Um, and we're going to be going through the second lab exercise, or the second, lab exercise, I guess you could call it. In the book that we're going through, the book is Learning the Art of Electronics, second edition. And we're doing, it's section 1N.24.3, which is applying the Thevenin model. And what we'll be doing today is making two versions of a circuit and verifying that they have the same attributes with regard to current and voltage. So yes, we'll be making two circuits, and then we'll be collecting their vital statistics, particularly their voltage and their current. And we want to see that they behave the same. So before we jump over to the bench and make the circuits, we're going to jump onto the computer here, and I'm going to show you the notes that we have for this part of the course. I should say what I might do today actually is just a little bit of revision. We went through the notes when I did the first version of, or the first circuit, which came out last week. But I kind of sort of just muddled through a little bit of the content there. So I thought I might have another go at it today. We'll be starting at the chapter 1N DC circuits. So I'll show you that now. So we're going to jump onto the computer, have a look at the notes. Then we'll jump onto the bench, make our circuits. Once the circuits are made, we'll test the circuits, and then we'll conclude. So let's jump over to the computer and have a look at our notes.
Here on the computer. And this is the ITL wiki in the lab with JJ wiki. We're working on Learning the Art of Electronics. That's the project that we're doing presently. I've got a little bit of explanation about that all up here. There's links to important parts of the project. There's some notes about the books. This is subscriber only content, the actual notes themselves. There's details about how to become a subscriber if you want to get access to those. You don't need to be a subscriber to access this page though, so feel free to come here. This is public access. Now, here is the table of videos that we've made. So we've done the introduction, and we did the first circuit, which was figure 1N23. What we're doing today is figure 1N24. So once this video is recorded today, the link will go here, and the show notes will pop up over here. If you want to do the pre-reading for today's material, if you want to follow along in the textbook, then read up to and including page 18. We'll be going through the notes for that in just a minute, but yeah, certainly recommend you get yourself a copy of the book and have a read up to page 18, which is where we're up to in our notes. So I'm going to just jump over here to DC circuits. I should say actually that I also made some notes. If I just scroll all the way back up to the top here, since the last time I showed you this page, the preface to the second edition and the preface to the first edition, I added some notes from the book. I think the overview was already done. So the part that we'll be revising today is DC circuits, starting here. And then when we get up to our circuit, which we'll be doing, we'll just transition over to the bench and make the circuit. So this is chapter 1N, DC circuits. N is for notes. This is the notes for the DC circuits lab, or day, I guess you'd call it, although I don't know, maybe lab, I'm not sure. Anyway, it's a chapter. The green stuff I'll just call out to you. So we're going to learn how to make a voltage divider. The subject of this course is the laws, rules of thumbs, and tricks that constitute the art of electronics. When delivering power to something, that something is called a load. This course is concerned with using electronics to model and process information, not so much to provide power to things. And the question is it better to model information with voltage or current? And the answer is that it's better to model with voltage, because if you model with current, you need to actually use power. With voltage, if you just measure, you don't need to use it as power. Ohm's law, should know this. V equals IR. V is for voltage in volts. I is for current in amperes or amps. R is for resistance in ohms. And they say a volt is what pushes an amp through an ohm. Equivalently, 1 volt is the work done as one adds 1 joule of potential energy to 1 coulomb of charge. Ohm's law is useful, but it only applies to resistors. Not everything behaves like a resistor. The inverse of resistance is conductance. So G equals 1 on R, the reciprocal of R, where R is in ohms, G is in Siemens. Okay, so then usually conductivity degrades increasing resistance when the temperature increases. It's not universally true, but it's usually true. So if you have 2 points separated by a distance d with a voltage V between them, the uniform electric field is given by E equals V on D. There are various strategies for making a resistor: carbon composition, carbon film, metal film, and wire wound. Many electronics components do not obey Ohm's law. Particularly, we'll see diodes and capacitors pretty soon, I reckon. Don't expect to use Ohm's law where it doesn't fit. It only works for resistors. We can extend the reach of Ohm's law with dynamic resistance. And that's given as the dynamic resistance is the change in voltage over the change in current. Then we can talk about the effective resistance of devices such as diodes, transistors, current sources, etc. And here's a map of a few things. The current source is interesting. It's just a flat line at 5. Of course, there's no such thing as an ideal current source that just goes to infinity. The resistor is just a linear line. Lamp and diode are curves of various types. Now this is plotting V against I, which is the opposite of how it's usually plotted. It's usually plotted I and V, and the reason why they flipped the axes here was so that the tangent comes out in ohms. So it's a rise over run, which is V divided by I, which is resistance. So the power is the rate of doing work. Components will have power ratings, so you got to be careful. They have to be able to handle or dissipate the power that you're going to be pumping through them. The formula for power in watts is given as P equals IV, or P equals I squared R, or P equals V squared on R. To find the minimum resistance for a quarter watt resistor at 15 volts, then a quarter watt equals 15 squared divided by R min. So R min equals 225 divided by a quarter equals 900. So 1 kilo ohm is close to the minimum safe value at 15 volts. Current measures charge per unit time, and voltage measures work per unit charge. So I times V equals work on charge times charge on time, which equals work on time, which is power. In this course, we rarely worry about power. And there's a bunch of references in here to the other material. We've got some references to Appendix C in AOE, Chapter 1 of AOE, Principles of Electronic Circuits, Electricity and Magnetism. So if you're interested in more reading, go and look up the details in those books if you got yourself a copy of them. Now we're going to talk briefly about Kirchhoff's laws. There's Kirchhoff's voltage law, KVL, and Kirchhoff's current law, which is KCL. So the KVL law just says that all of the voltages are in a circuit sum to 0. So the sum of voltages around a loop is 0. And the current law is that the sum of currents into a node is equal to the sum of currents out of a node. And then for series current, you have the total current is the same as I1 and I2, whereas the parallel current total is the current through 1 plus the current through 2. A series voltage, the voltage total equals V1 plus V2, and the parallel voltage, V total equals V1 equals V2. Applications of Kirchhoff's laws, series and parallel circuits, a couple of truisms probably already familiar to you. Fair enough. Now here they're just showing you that even though it's not clear that this is a circuit, it actually is a circuit. So the whole thing, you need to know that ground and connects up to the negative side of the supply, and it's actually a circuit. For parallel resistances, the conductances add, the resistances don't. So because the conductances add, the total conductance is conductance 1 plus conductance 2 equals 1 on R1 plus 1 on R2. And if you're solving that for a network of 2, then the total resistance is given as R1 times R2 divided by R1 plus R2. And here's some easy cases. So if you've got two R's and they're the same, then you're going to see half of R. And then if you've got R and 10, then you're going to get 10 elevenths of R, which is 0.91. So it's very close to R. And 2/3 of R breaks out in this way, so you get 2/3 of the resistance if you've got two here and one here. So as they put it here, in a parallel circuit, the much smaller current dominates, which is smaller resistor dominates, and in the series circuit, the larger resistor dominates. So that's good to remember. There's a note here that when you're using a potentiometer as a variable resistor, you should tie one end to the wiper. A potentiometer is a 3-terminal device, and if you only need a 2-terminal device, apparently there's good reasons for tying one end to the wiper. I forget what those were now. But if you want to know, you can look up the chapter 1N3 and have a read for yourself. And then you can jump on YouTube and tell us in the comments section. Some compact potentiometers are made with Cermet, which is a composite material made from ceramic and metal. Now this is a voltage divider. So we've got 30 volts coming in here, we've got 10k resistance here and 10k resistance here. So the 30 volt comes in, 15 of it, which is half of it, drops across here, and then there's our V out, gets 15 volts, and the rest of it drops across here. So this is a voltage divider. You will become very familiar with this type of a circuit. There's a whole section on voltage dividers in the Art of Electronics, so jump over there and check that out if you've got a copy of the book. We're going to be analyzing a voltage divider like this. This looks very much like the one we saw already, but the details have been taken out of this one. There's no specific numbers on it yet. They're talking about 3 ways to analyze this circuit. So you can calculate the current through the series resistance. For the current is V in divided by R1 plus R2, which is 1.5 milliamps. After calculating the current at 1.5 milliamps, you use that to calculate the voltage in the lower leg of the divider, which is the output here equals the current, which is 1.5 milliamps times R2. In this case, that's 1.5 times 10, 10k, which equals 15 volts. But they say that this method of figuring out how the divider behaves takes too long. So here's another go at it. The second method, you rely on the fact that I is the same in the top and the bottom. So this is I coming through here. That's what that I there is. and then the current through here and the current through here is the same, because the current's the same everywhere in a circuit like this. So the voltage divider, second method, we're using the implicit current. So you get an expression for the voltages, and you can rearrange it in terms of currents and resistances, and then you can figure it out in resistances, because the currents cancel. And then that leads us to 1N1, which is the first equation that we have here. So this is equation 1N1, and it says that the output voltage, which is at this point here, is the input voltage times R2 divided by R1 plus R2. So that's this voltage times this divided by this plus this. And in this case, that means this, which means you get half the voltage. So as it says here, you will use the formula 1N1 fairly often. There you go. And then the third way that they encourage you to think about it is not to do any mathematics at all, but just muddle through with saying to yourself something like this. Since the currents in top and bottom are equal, the voltage drops are proportional to the resistances. Later, impedances, a more general notion that covers devices other than resistors. So in this case, where the lower resistance makes up half the resistance, it will show half the total voltage. And then they give you another example here. If R2 is 10 times R1, then it will show 10 out of 11 of the input voltage, which is roughly 91%. So now we're going to talk about loading and output impedance. We're going to get to it in just a minute, but I'll tell you straight away that output impedance of this part of the circuit and the Thevenin resistance are the same thing, at least for DC that we're dealing with at the moment. But we'll get to that in just a second. So we need to think about what we would do if someone comes along and adds a load here, a 10K load, to our circuit. So this is our circuit over here, and someone attaches a load. We need to power the load with our circuit as a power supplier. Yes. So they suggest two different methods of calculating the V out. So you can model the two low resistances here as one, which becomes 5K because they're in parallel. Then you can calculate V out for this new voltage divider as seen in figure 1N20, which is here. So here's this re-expressed as a parallel resistance. And then we see that when you've got 5K here and 10K here, then the new divider, which is this, delivers 1/3 of the input voltage across here. That's 5 here, 10 here, so it's 5 out of 15 equals 1/3 of V in. And as they say, this method requires you to draw a new model for each possible loading. So every time you change this bit, you need to recalculate this bit and do the whole thing again. They don't want us to do that. So the better method is to use Thevenin's model, which is where we calculate an equivalent circuit. There's two elements in the Thevenin model. There's the Thevenin voltage and the Thevenin resistance. And we take a model like this, which is a voltage divider, and we ignore the load. The load is not part of the Thevenin model. And then we re-express that as this. The Thevenin voltage is the open circuit voltage here when no load is attached. So there's no droopiness from an attached load. It's the unloaded voltage, or as they call it, the open circuit voltage. And the Thevenin resistance is just R1 and R2 in parallel. So this is R1 and R2 in parallel, and that's the Thevenin resistance. So the voltage is the open circuit voltage, and the Thevenin resistance is R1 in parallel with R2. And then there's a box here, Thevenin's good idea. Model the actual circuit unloaded with a simpler circuit, the Thevenin model, which is an idealized voltage source in series with a resistor. One can then see pretty readily how that simpler circuit will behave under various loads. So they go on to say what we just said, which is the Thevenin voltage is just the open circuit voltage. The voltage when nothing is attached, that is with no load. And the Thevenin resistance can be formulated as the quotient of the Thevenin voltage divided by the short circuit current, which is the current that flows to ground if you simply short the output to ground. But we don't do this. We don't actually short this to ground. In practice, you won't find Thev by shorting the output to ground, and doing so can be dangerous. So don't do that. Shortcut calculation of Thev, the Thevenin resistance. So, given a circuit diagram, the fast way to calculate the Thevenin resistance is to see that it is the parallel resistance of several resistances viewed from the output. So the output is here. This formulation assumes that the voltage sources are ideal. When they are not, we need to include their output resistances. For the moment, we ignore this complication. Cool. So basically, R1 parallel to R2 is Rthev. All right, now justifying the Thevenin shortcut. The shortcut shown in figure 1N.22, which is this, asserts that the Thevenin resistance equals the parallel resistance, but this result may strike you as a little odd. So why should these be equivalent? And then they go on to do some discussion there. I didn't completely understand it, to be candid. But basically you can just treat them as parallel. Apparently we'll be doing this quite a lot. A general definition and procedure for determining the impedance at a point is to apply a change in voltage and measure the change in current. And then you can just divide V by I, and you get a quotient, and that quotient is the impedance. And that's the dynamic resistance. And it's something that we did. It was what we did in our last circuit, which is here. We're just about to come up to it. So the figure 1N.23, which is the subject of the first video, this is the second video. So the first one, the one we did last week, was this 1N.23. Uses the small signal or dynamic version of Ohm's law. In this case, 1 milliamp was flowing before the wiggle. After we force the output up by 1 volt, the currents in the top and bottom resistors don't match. The reason for that is there's an extra current induced by our new power supply, the wiggler. And we can calculate the impedance, and this is what we did in the last lab. We got 1 volt divided by 0.2 milliamps equals 5 kilo ohms, which is what we would expect to get if we took the parallel resistances. 10K and 10K will give us 5K. Our measured current stacks with what we'd expect from the model. So again, we apply wiggle voltage delta V, and we see what delta I results. Rationalizing Thevenin's result, parallel R's. Any non-ideal voltage source droops when loaded. How much it droops depends on its output impedance. The Thevenin equivalent model with its Thevenin resistance describes this property neatly in a single number. So the Thevenin resistance is the output impedance. They're the same thing. So the output impedance of a circuit and the Thevenin resistance of a circuit is the same number, meaning the same thing, and you can use it to determine how much droop there will be in the supply voltage based on how much load you attach, whereas the load is in a resistor. essentially. So now here's a little innovation that that I've been introducing in the notes. I don't know if I'm going to keep doing this, but I asked ChatGPT, are output impedance and Thevenin resistance the same thing? And it said the short answer is yes. In practice, they're the same concept. And then it went on a whole lot to talk about the various impedances and resistances and such. So the bottom line was the output impedance and the Thevenin impedance are the same thing. If you're only dealing with DC or resistive cases, then the Thevenin resistance is the same as the output impedance, which is what we're dealing with at the moment. And at last, we're up to today's circuit, which we'll be doing. This is Fig-1N.24. This is in the section called 1N4.3, applying the Thevenin model. So what we're going to do here is we're going to make sure that Thevenin had it right. We're going to make sure that the model behaves the way the original circuit does. So this is the original circuit, and this is the model, and we're going to make both of them, and then we're going to test point A, B, and C, and point A, B, and C, and we're going to compare the voltages and currents through these points or across these points, and see that they stack up. So that'll be 3 voltage measurements for each circuit, and 3 current measurements for each circuit, and 2 circuits that we're going to make. We won't be able to use the same voltages that they've used here because I don't have a power supply that goes that high. So we'll scale them back to like half or third or something like that. Anyway, we'll figure that out together in just a minute. So so we want to find that the 10K 10K divider, when given 30 volts, put out 15 volts when not loaded, and drooped to 10 volts under a 10K load. See figure 1N24. Does the model do the same? So that's what we want to just see. We want to see it loaded and unloaded, I guess that means that we'll have to be able to attach the load or detach the load. Fair enough. So I'll have a think about that when we're designing the circuits now. So that'll be 2 circuits, and we'll be able to put the load in or take the load out. That'll be important. So I'll have to think about which points we actually keep. And we're expecting to find that the model droops to the extent the original did. So that's a spoiler alert. That's what we're hoping to show, down to 10 volts given the ones that they had, but we won't be using the same voltages, so ours will scale down by some factor. So what the model provides that the original circuit lacked is that single value, the Thevenin resistance, which expresses how droopy/stiff the output is. And I asked ChatGPT the question, if output impedance measures how stiff or droopy an output is a higher output impedance more droopy or more stiff? And the answer is it's more droopy. So if the output impedance goes high, the voltage goes droopy. So higher output impedance is less stiff. The output voltage sags more under load. So there you go. And then it goes on to explain that with a whole lot of mathematics and compares 2 cases, one where R out is 1 ohm and one where R out is 10 ohms. And they just get the different load voltages as 4.5 or 2.5. So you can see the second case sagged considerably more than the first case. And then we're up to the further notes. So we'll take those on later on. So today we're concerned only with this circuit here, or 2 circuits really, with the load switched in or out. So let's jump over to the bench and make these circuits.
All right. Well, here we are on the bench. I thought I might show you this. This is my decade box. It's a variable resistor. You just switch in the resistances that you want, and it puts them across the terminals here. So I only have one of these, and I found myself wishing I had two of them so that we can do some of the labs that will be coming up soon. So I bought myself another two of these, so I'll end up having three of them. I probably only really need two, but that's good, and that will replace these. I do actually have two of these, which are also Decade boxes. But unfortunately, this one can only go to 100k max, whereas this can go to 10 mega ohm max. So, and this one is big and bulky and awkward, and this one is less so. They're both pretty weak. They're only quarter watt solution, so you can't put a lot of power through this thing, which is a shame. I wish they had have got ones that were higher power. I'm not sure why they made them so so anorexic. I don't know. Anyway, the other thing I suppose I should mention is that I bought this analog multimeter because they talk about the VOM, the volt ohms milliammeter, the venerable VOM, which is the old analog meter type meter. But I didn't realize when I bought it that it was going to be so pokey and cheapo, and it's just this one is it's awful. But no, yeah, I couldn't get the specifications that I need. I didn't understand it. So what I've done is I've bought another one. So we'll be covering that when it arrives in the mail in the not too distant future. And then once that's done, we'll use it. So this one is just going to go into the scrap heap. Really, put it in the corner. It might come in handy one day. Who knows? Anyway, give me 2 seconds. I'm just going to duck away for a moment and come back with all the bits we need for this circuit we're building today. All right, well, I'm back. I got a bunch of 10k resistors, and I got these ones which are 5.1k resistors. I can't get exactly 5k at the moment. I have ordered some 5k, I think, so those should be turning up someday, but for now we'll just use 5.1k. It's close enough, is good enough. They're 1% resistance. Anyway. So here is our wire, so we'll be needing some of that. And these are our resistors, very good. These are our power terminals, and these are our circuits. So before we get started, let's turn our soldering iron on, and let's put some water in the soldering iron sponge. That'll be a good idea. It's pretty good to me. Gonna want to hit it with a bit of isopropyl and a cotton bud or a Q-tip, as our American friends like to call them. So just a little bit of cleaning off of the old circuit board. So, I guess we might as well just put it in time-lapse mode. I'm going to be making two circuits. I suppose before we do the circuits, I might as well just show you what we'll be doing. So, where's that book? All right. Can you see that? You can. That's good. Now we're up to page, I think, 18. Page 17. Okay. So what we'll be making is these two circuits here. And we want to be able to switch the load in or out. So that's what we'll be doing. So I'm going to put these two circuits together. I'll do it in time lapse, and then I'll report back when we're ready to go. All right, well, I'm not sure what happened there. I just built this circuit. I was supposed to be time-lapsing it, but I think maybe I wasn't recording when I put it together. Anyway, it's put together now. So this is the first circuit that we'll be doing. It's the actual circuit as opposed to the Thevenin model, which we'll also be building. So this is the first circuit for us to test. And let's just draw up our testing system. We're basically going to run the numbers with load and with no load. So I've got this jumper down the bottom here that can optionally attach or detach the 10K load. We should be able to get our 3 readings for each of the points, and the points will be similar for both. So we're just basically going to start here, and we're going to go V A B, and then we're going to go V B C and V A C. I'm going to do I A, I B, and I C, which will be the current through those points. And then we're going to have no load and load. And then we're going to do it all again. And we're going to have no load and load. I called this one D1 and this one D2. D was for design. I was going to call it circuit, but I've already got a C, so I just called it D. So this will be D1, D1, and this will be D2. All right, so I might just quickly fix this up. Hang on. All right, so I just fixed up our thing there. So we haven't built this circuit yet. Will we build that circuit now? Why not? I'll just I'll time lapse that build, and we'll come back when we've got both circuits ready. All right, so I've made the 2 circuits that we'll be using. So now it's time to break out the multimeter and take our 2 sets of measurements. So we're going to do a set of measurements with load attached. It kind of doesn't make any sense to have the second model without a load, but it's possible to remove it. So we'll run the numbers anyway, but I don't think we should expect them to make sense. So we're going to do D1 first. I've labeled them, by the way. There's a D1 and D2, design 1 and design 2. Of course, D1 is the actual circuit, and then D2 is the Thevenin model of the circuit. Yes. Okay. Well, let me get the multimeter. Hang on, I'll be back. All right. So I've got the old multimeter out, and it's got the DuPont female ends for attaching to our circuit. This is D1. We're going to do that first. We're going to model it first with no load and then with load. So to detach the load, and we're going to have to be careful too that we've actually built this circuit correctly. So if we get some strange readings, we might have missed a wire or something. So what we've done there is disconnected the load. So there's no load. So we want to get the voltage across A and B. So let's do that. A and B. Oh, of course, we've got to power the whole thing. Dear me. Now, the power is going to be different than the thing said. So it said 30 volts, but we're going to run in 10 volts. Just because I can't deliver 30 volts with this power supply that I've got here at the moment. Let me throw you over to that camera, by the way. Just a sec, I'll be back. All right, so here's the power supply. We've got it set at 10 volts. There's not really much else to show you. It's constant voltage, so the current settings don't matter. The over voltage is not likely to be a problem, but we've got it set at 20 volts and 1 amp. If it goes over that, it'll shut down. So, sorry, back over here. All right, so you can see the bench here, and up in the corner there is the power supply. All right, so we run the power in here. It's not turned on at the moment. All right, so now is the moment of truth. We turn on and, okay, we're not seeing anything. What's the problem? Huh. Huh. Up there. Up. Yep. We're missing one jumper. All right. So I'll put the iron back on. I'll fix this up and I'll be back. All right. So I just put in that extra little jumper there. So let's attach power again, and we'll put on our probes. This time, hopefully, it will work. Put the positive one on there and the negative one on there, and that's testing the voltage across A and B. We're in voltage mode with power on, and we've got 5.018 volts, which is an encouraging reading, isn't it? So 5.017. 5.017. All right. Now we're going to be doing B to C. So there is C. There is B. And that is 4996. 4.996. And then the voltage between A and C should be the full 10 volts. 10.02. Now we're going to do the current through A. Okay, so let's turn our power off and take out our jumper for A, and then attach our current probes and put the device in microamps range with microamps connector, power on, and we're seeing 501. 501.6. 501.6 microamps. All right, and then the current through B, so we'll turn him off, take him out and put him back on there. And then we'll put off point B, and we'll put in our current probes for B, and power on. And we've got no... What have I done wrong? I did this last time as well. There we go. All right, so it's 501.6, exactly the same. And then we're going to want to do the current through C. So let's put him on there. And with the same 501.5, 501.5. That's what we wanted to see. All right, so we're going to we're going to take our set of measurements again for this circuit, but we're going to attach the load this time. So the load's attached there. That's what the white jumper's for. So I'll turn our power off. We'll put this guy back in voltage mode. All right, and we're going to be testing the voltage between A and B. A and B. All right, on we go. And the voltage is 6.67. 6.67. All right, and then between B and C, we've got 3.338. 3.338. And VAC should be 10, I think. Yep. 10.02. And then we're going to do the current. So we're going to have to turn our meter off. We'll put him back in microamp mode. Attach that there. I'll pop out the first one. So we want to get the current through A, which is there and there. All right, so we'll power him on, and we're getting 666. Dear me, 666. And then we want to do the current through B. And what do we got? Same again. 666. And then we want the current through C. So we're going to turn him off, put him back on there, there. And the current through C is 334.1. 334.1. All right, so that concludes testing for the D1 circuit. So we'll put him in the drawer, and we'll put this guy next. Now we're going to have to power him up, which is all well and good. Now we're going to do one set of measurements with the no load, and then we're going to do a set of measurements with the load. The no load won't complete the circuit, I don't think, so I'm not sure exactly what we'll see, but we'll see soon enough. All right. So we're going to start with some voltage readings. So we'll put our device back in voltage mode. All right, and let's hook up the voltage probe, A and B. All right, and we power him on, and we're not reading anything. Okay, so I've forgotten to connect something by the looks of it. Strange. I'm not seeing a problem. What's the problem? It's because the load's not connected. So does it even make sense to have? I tell you, we won't do these no load readings. I did say that. Yeah. All right. So we're not gonna take if we take the load out of this circuit, then there's no power. You need the load for this circuit. So we're just going to test just the load column. Okay. So, well, I guess we could. No, yeah, okay. We're going to measure the load. So we're looking at 3.373.
3.373. And then BC. BC. 664. Those numbers are the wrong way around, aren't they? And then AC. 10.02. So they're the right numbers, but they're on the wrong ports. So I've obviously jumbled that there. All right, now we're ready to do the current measurements for the D circuit. So we'll put him in microamp mode. I'm not sure what his problem is. All right. So we're going to be doing the current through A. Current through A. There we go. On we go. And what are we measuring? 661. 661. And then we're going to want the current through B. All right, that's 661 as well. 661. And then we want the current through C. Okay. And that'll be 661. 661. All right, so I'm going to close down this experiment. We're all done. All right. Well, let's have a look at the numbers. Before we do that, I'm going to take a quick break. I'll be right back. Well, I think I'm heading towards wrapping up this video, although I have to say I don't completely understand what we've done. It doesn't make sense to have this circuit without the load, because the load's the only thing that completes the circuit in this system. So if we took that away, there would be no ground, there would be no circuit. So what am I trying to say? These numbers are the same, but they're the wrong way round. So I've obviously labeled these points incorrectly, which makes sense when I sort of think about it, because the Thevenin circuit is these two, and then there's this and this, but then there's also that down there. So this whole thing is actually a voltage divider as well. So I think these points aren't equivalents. So actually, there you go. And this is the droopy voltage, which turns up here between here and here, right? So B to C here is the same as A to B here, and we do see it droops the same amount. This down here I can't account for, the current through C, but I'm not going to think hard about it because I don't want to. Is that a correct reading, or did I perhaps bollocks the wiring in some fashion? It's all the same over here. I'm not sure why it's half here. I don't get it. But I'm going to call this one a wrap.
then tie it off and send you over to the farewell cam and get it published. And we'll be back next Tuesday for the next installment. And that's a wrap. So, okay, second circuit completed. We sort of muddled through towards the end there. I don't understand why we got that weird current reading. But basically we saw the droop in the two circuits, so they do seem to be equivalent. We'll have to fuss over naming the points though, because they don't translate easily. But yeah, there we go. So learning about the Thevenin resistance and the Thevenin voltage and the model of the voltage divider. So getting more experience with it, getting a better intuition for how it all works. There's still more, it's further to go, but we've made some progress. So I'll get this up, I'll get the notes published, and I'll get the recommended reading for the next video as well. It's not going to be much, just a couple of pages. As the next thing we're going to be doing is checking a bunch of voltage dividers that use the same proportions, 50-50, but more or less resistance. So we'll do that when my new decade boxes arrive, which should be this week. So it should be ready to go for next Tuesday. So yes, I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.